Now, I just want to make a very quick distinction between negative acceleration and deceleration. Now, deceleration occurs when you slow down, when the acceleration is in the opposite direction of the velocity. So, for example, this car right here is traveling to the left with a velocity of 15 meters per second to the left. That's in the negative x direction. See the negative sign right there? And it slows it down. It's now traveling 5 meters per second, still to the left, still with a negative sign. So it has experienced an acceleration that is in the positive x direction. It has experienced a positive acceleration, yet it has slowed down. So it has decelerated because the acceleration is in the opposite direction. Negative acceleration occurs when the acceleration, as defined by the coordinate system, is in the negative direction. If the car in this example right here was traveling to the right rather than to the left, and it experienced the same acceleration, then it would have increased its speed. Now, much like velocity was the change in position, acceleration is the change in velocity. And if I say, let me take a look at this bug, and when is that bug accelerating, and I draw the bug's velocity vector through all these points, and say each one of these points occurs, at a 1 second interval. Where is the bug accelerating? Well, right here, the bug is in a constant velocity state. Now, as the bug changes its direction, the velocity vector also changes. And now the spacing of the bug starts to increase, as well as the direction of it changing. And lastly, the velocity vector gets smaller and smaller and smaller. So right here, the bug is at a constant velocity. Constant velocity meaning is not accelerating, so there is zero acceleration. The velocity vector changes in 2, 3, and 4. It changes direction in 2, it changes direction and length in 3, and it changes length in 4. So the bug's accelerating in 2, 3, and 4. Much the same with instantaneous acceleration with instantaneous velocity. If I look at the change in velocity divided by the change in time, as I choose my time increments smaller and smaller and smaller, then I get a measure of the instantaneous acceleration. So for example, if you're at a stoplight and you punch the gas and your car works its way up to a certain speed, it changes gears. It's not accelerating as much when it changes gears. And then you continue your acceleration. Your average acceleration will be a certain number. However, if we start to look at smaller and smaller and smaller time intervals, then maybe the instantaneous acceleration may not be the same number. Now, motion at a constant acceleration, this is a very important topic right here. If we take a look at the average velocity of an object that's traveling in a certain time interval, average indicated by that bar right there, we look at the change in position divided by the change in time, and the book's written that kind of like that. And if we choose the initial time to be equal to 0, then we write our average velocity to look like that. Now, we can rearrange this. We can say that the average position, or that the position is equal to the average velocity multiplied by time plus the initial position. Very often we choose that initial position to be 0. And if this object is accelerating, then we can write its acceleration just like that, and we can write its the velocity in terms of the acceleration, where it's the acceleration times time plus the initial velocity. Now, if I want to think about my average velocity, then that is actually going to be the final velocity plus the initial velocity divided by 2. That's just the definition of average. So here we've gone ahead and we've written the average velocity like that, and I'm going to combine these equations right here. This is the equation that I wrote regarding the position as a function of the average velocity, and we plug that average velocity in right here, and we come up with this equation. And then remember that we wrote that the velocity was equal to the initial velocity plus the acceleration times time. We did that in the last slide. So I'm going to do that right here and replace the velocity by the initial velocity plus the acceleration times time. And we do a little bit of algebra and we come up with a very important equation describing the position as a function of time. And you'll note that there's actually a time squared here. This is a quadratic. So you might want to go and take a look at the your old algebra notes about how to solve a quadratic equation. If, for example, I gave you the position over here and I asked you to solve for time, you need to use the quadratic equation to do that. Now you can also combine those equations such that you eliminate the time variable and you come up with this equation right here. I'm going to spare you the gory details from that, and we come up with 4 equations that describe all the kinematic motion in one direction. Very important equations. You're going to definitely want to have these written down somewhere, and as you go ahead and you solve problems, you want to look at these equations and see what you know, see what you don't know, and see what you can solve for. Okay, solving problems. Now, in order to solve the problem, the very first thing you want to do is read the problem twice. The reason why you want to read it twice is because you want to make sure that you understand it. This leads directly to number 3. Scratch this. Now, solving problems. The first thing you want to do is read the problem twice, because you're just not going to maybe grasp everything that it's asking with the first read through. For example, you might see the word, free falling, and that is going to more than likely mean ignore air resistance. You might see the word smooth. That might mean ignore friction. So read the problem twice, make sure you understand it. Decide on what objects are under study and what the time interval is. Now, the book doesn't do anything too tricky, and I'm not going to do anything too tricky by giving you a whole bunch of different meaningless objects and letting you figure out which one's important. So fortunately, this one isn't a big one. Drawing the diagram is important. If you're drawing, for example, a car accelerating, you can write down its velocity initial, you can set the time initial, and then you can draw it again at some later date or some later time and the relevant parameters with that. If you're drawing forces that are on a box and you're trying to figure out which forces are acting where, having a little drawing really does help. And then of course you choose your coordinate axis, you choose those to make your life as simple as possible. Now write down everything that you know. Since this is one-dimensional motion, we're going to probably know position, we're going to know velocity and acceleration, and we might know, the second one, the initial one, the second one, the initial one, and the initial one. Write down everything that you know, maybe even put them in a table. Think about what physics applies to this problem and plan an approach. Since you've already written down all of the knowns and also unknowns. What do you need to know? Are you looking for a position? Are you looking for a velocity? Are you looking for acceleration? Now you can write down which equations you have, and we have the equations from a couple of charts ago. It really helps just to have those 3 or 4 equations off to the side. Which of these relate to what you know? Are you looking for time? Are you looking for position? Are you looking for velocity? At that point, you can identify which equation you need to use based on the knowns and the unknowns, and it's a simple matter of solving the problem algebraically for the unknown quantity. Check that your result makes sense. Round it to the nearest number of significant figures. I'm not going to beat you up too badly over that. And last but not least, is it reasonable? I mean, if something is free falling for 10 seconds and you get a velocity of 1,000 meters per second, does that make sense? I mean, that's 1,000 meters per second is pretty fast. So, I mean, does it fit with your intuition or a rough estimate? And last but not least, do pay attention to units. I'm not a big fan of doing unit conversions, but the problems in the books sometimes makes you do that. Now, freely falling objects, falling balls. If you have a ball, it is going to accelerate downwards towards the earth. All objects experience this acceleration due to gravity. So we have some acceleration, and that is due to gravity, which occurs at a rate of 9.8 meters per second squared. Very important number to remember. You're going to be using this number a lot. Now, this is an example of motion with a constant acceleration, and you can say that the ball is going to initially start from rest, and it's going to start to fall. It's going to initially have 0 velocity, and the velocity is going to increase and increase and increase and increase, but also the position, the distance that it changes per unit time, is also going to increase. This means that the velocity is changing. It means that it's accelerating, and it's accelerating at 9.8 meters per second squared. Now, just an aside, the last slide mentioned units. Our position will always be in meters. Our velocity will always be in meters per second, and our acceleration will always be in meters per second squared, at least using the SI system.